This lecture is on capacitors. When a battery is connected to a capacitor, charge moves between them. Every electron that moves to the negative plate leaves a positive nucleus behind. As the plates charge, the potential difference between the plates increases. The current through the circuit decreases until the capacitor becomes fully charged. The plates have equal amounts of charge, but one is going to be positively charged and the other will be negatively charged. Looking at the diagram here, if we were to actually have the capacitor charge by closing this switch, what happens to the brightness of the bulb? Go ahead and pause the video and write your answer down. Okay, so let's take a look. While the capacitor is charging, its resistance is increasing, so the current in the circuit will decrease. Therefore, the lamp gets dimmer until the current stops and the lamp goes out. If the battery is now disconnected and current is allowed to flow, the capacitor discharges. The current decreases until the capacitor is fully discharged. The potential difference decreases until the capacitor is discharged. Now what happens to the lamp? Go ahead and pause the video and answer the question. Okay, so let's take a look. As the capacitor decreases, the voltage on the plates, the potential difference will decrease, causing the lamp to start out bright but get dimmer until the capacitor is fully discharged and the lamp goes out. This statement right here, as the capacitor decreases, this is incorrect. The capacitor doesn't decrease anything. Its capacitance remains constant. It's that the potential difference, or the charge stored on each plate, changes. In which of the following circuits will the capacitor store charge if the battery is disconnected? We don't mean to continue to store charge. We mean it's already charged and will continue to stay charged. Go ahead and pause the video and select your answer. Remember, there's two. Okay, so let's take a look. If you look at the circuit, hopefully you chose B and C. If I disconnect the batteries here and replace it with a Y, just leave it there, the charge on the two plates of the capacitor remains the same. It doesn't move. If I remove the battery here, though, what happens is that this capacitor will discharge through the resistor. If I remove this battery here, nothing happens to the plates. If I remove this battery here, the capacitor will discharge through these two resistors. So let's talk about equivalent capacitance. Circuits can be redrawn as if there were only a single capacitor and a battery. By reducing the circuit this way, the circuit becomes easier to study. The process of reducing the resistors in a circuit is called finding the equivalent resistance. For capacitors, it's finding the equivalent capacitance. The capacitance for capacitors in series will be CS, and the total equivalent capacitance in parallel wired capacitors will be CP. What is the voltage across each capacitor? What is the charge on each capacitor? Okay, in order to answer the first question, you have to use Ohm's law. Go ahead and pause the video and see if you can answer these. Okay, so let's take a look. If we look at C1 and C2, this is connected to the plus plate. This side is connected to the minus plate. These two capacitors are wired in parallel, and that means the voltage across each capacitor will be the same. So what does that mean about charge? Well, remember, charge is equal to, Q is equal to CV. Okay, so the charge is going to be VC1, and the charge here will be CV2. C2V, and this will be C1V. The voltage across the capacitors is the same. The charge will add up because here we're going to have Q1, which is equal to C1V, and this is going to be Q2, which is going to be C2V. Since V is the same for both capacitors, we can replace the charge Q with CV. Notice that if we divide through by V, we get the total capacitance, which means that we add up the capacitance when the capacitors are wired in parallel. Notice that this is the opposite of resistors wired in parallel. For a series circuit, we have V1 and C1. The Q is going to be the same on both plates. And that means that if we replace V, which is equal to V1 plus V2, with Q over C, we end up with Q over C equals Q1 over C1, which equals Q2 over C2. The Q is all the same though, it's the same charge on all the plates. So the Q's cancel out, and we're left with the equivalent capacitance is equal to the sum of 1 over Ci. Now, we also have to take the inverse of this total sum. So when we take the sum of the inverses, we then have to inverse that in order to get the equivalent capacitance in series. Finding the equivalent capacitance is like finding the equivalent resistance, only reversed. In capacitors in series, you can see the relationship here. 1 over the total capacitance is equal to the sum of 1 over Ci, where we're counting from 0 to whatever I value of capacitors we have. And for adding up resistors, this should be an R, not a CP. This should be an R in parallel, and notice it's the same form. So when we have capacitors in series, it's the same as adding resistors in parallel. When we are adding capacitors in parallel, it's like adding resistors in series. What is the equivalent capacitance in millifarads if C1 is 4 millifarads and C2 is 6 millifarads? Go ahead and pause the video now. Okay, so let's take a look at your solution. Remember that these these capacitors are wired in parallel. That means we're going to add them together. So the equivalent capacitance is going to be 4 millifarads plus 6 millifarads, which gives us 10 millifarads. What is the equivalent capacitance in millifarads for C1 equal to 4 millifarads and C2 equal to 6 millifarads? Okay, go ahead and pause the video. Okay, so let's take a look at your solution. Hopefully you took the inverse of each capacitance and then added them together. This gives you an equivalent capacitance of 5 over 12 millifarads. We then invert that, and that gives us 12 over 5 millifarads, which is 2.4 millifarads. What is the equivalent capacitance if C1 is 5 microfarads and C2 is 11 microfarads? Go ahead and pause the video. Okay, again, they're in parallel, so we're just going to add them up. You should end up with 6 millifarads. For 42, I'm not going to go ahead and go over this, but again, the answer, if you already did it, should be 2.25 millifarads. In the next video, we'll cover RC circuits.